Hey everyone, I'm Joachim, and today we're going to create a custom Vellum emission setup that recursively emits soft bodies on simulation time. This video will be split up into two different parts, and in the first part we're going to create the actual simulation, and in the second part we're going to do some post-processing to make sure that our sim is ready for render. There's lots of topics to cover in this one, so let's dive right in. Here in Houdini, we're at the geometry level, and I've just gone ahead and created some base geometry that we'll be using to instance into our simulation. There's nothing special really, just simple geo operations, beveling, extruding, adding some normals and UVs, and subdividing. I am, however, using a match size node, just to make sure that the size will be a unit of roughly 1. So all the instances should roughly be the same size. The absolute first step will be to prep our geometry for simulation. I'll merge these geometries together. And then I'm going to append a connectivity SOP. And I'll switch the connectivity type from point to primitive. So with the connectivity SOP, we can use the class attribute to create a unique name for each object. And the way we can create that is by creating a new primitive wrangle. And in here, we can initiate our name attribute. And we can say that we want this to be called piece plus our class attribute, which we need to convert from an integer into a string with the i2a function. So now if we check our geometry spreadsheet, we can see that we have a unique piece for each object. I'll just rename this to init name so that we know what this is for. And then we can run some operations individually on each object. And we can do this with the for each loop. And the one we want is the for each name primitive. In here, I'm going to start by remeshing. And then I'm going to change the target size to 0.08. And I'll also up the iterations to 4. After the remesh node, I'm also going to add some tetrahedrals. And we can do this with the tetconform node. And I'm also going to copy the target size from the remesh node and paste it into the max tet scale as a relative reference. I'm also going to remove the UVs because we don't really need them in the simulation. I'll then add some normals. Set this to by face area. And I'm also going to pack these. And in here, I'll just want to make sure that I transfer that name attribute that we created earlier. Next, I'm going to want to create an attribute with the approximation of the diameter of each object. And the way we're going to do this is by dropping down another wrangle. This time we can use the point wrangle. So we can write vector min, and then we can do the function get bb_box_min. And this needs the current geometry stream that we're working over, which is 0. And then I'm going to copy this, and then I'm going to do the same for the maximum. Like so. And then, in order to get the approximation of the diameter, we can initiate a new variable, call it diameter. And then we can take the length of max minus min. And then I'm going to write this out into an attribute that we can use later. We can then drop down a null and label it out instance source so we can bring this portion of the network into DOPS. All right, cool. So now we prepped the geometry. So let's head into DOPS. I'm going to start by dropping down a DOPnet. So here in DOPS, we'll start by setting up the basic components needed for Vellum to run. First, we need the Vellum object. And then we're going to need the Vellum source, as well as the Vellum solver. Pipe in the Vellum object to the left and the Vellum source to the right. I'm also going to set up a ground plane as well as some gravity force. And I'm using the pop force here, but I'm just grabbing the gravity value from the gravity DOP. So the sourcing will be done by the Vellum source node, but we'll do the actual sourcing in a SOP solver so that we can access the DOP geometry and constraint geometry on each simulation step. However, the activation field in the Vellum source node will control when we want to feed new geo into the sim. So this slider here will toggle on and off. I'm going to use an expression to do this for me. All right, so let's go through this expression. So since my start frame is at 1001, I need to shift the frame value by 1000 in order for this modulo function to work. But if your frame starts on frame 1, you can change this to $f and it will work the same. So we're using a modulo function, and this essentially says that this should emit every other frame. We can change this to emit on every 4th frame if we want, but for now I'm just going to leave this to every other frame. So if this section is 0 or the current frame is the start frame, it will return 1. So we're making sure that we're emitting on the first frame and then from there on every other frame. So as mentioned, the actual sourcing will be done in a SOP solver. So the SOP solver will create the Vellum geometry and the constraint geometry that will then reference in the Vellum source node. So if I create another merge node, and we're in here, the first merge node will be our forces. Then we can drop down a SOP solver. So by default, the SOP solver is set to work over the geometry, but I actually want to work over the constraint geometry in this case. And then I'm going to make sure that I hit the solve objects on creation frame. And I'm also going to drop down a gas intermittent solve. And this will make sure that we're only running the SOP solver on every frame and not every substep. All right, so in the SOP solver, we're going to set up the spawning logic as well as adding the Vellum constraints needed by the solver. And right off the bat, we get a DOP import SOP, which is currently set to bring in the constraint geometry, and that's fine. However, the geometry we want to use as a base to scatter points on is actually the geometry. So I'm going to make a copy of this, and then I'm going to delete this string here and just explicitly call the geometry. So this will now bring in the geometry, and this will just be running the constraint geometry. I also don't need these nodes, so I can just delete them. So the way we'll be adding new geometry into the simulation is by scattering points on the already simulated Vellum geometry. So what we'll get is a simulation that is feeding new geometry on itself. But there's a gotcha. On the first frame, there's no geometry available that exists. So we need to make sure that we start off the simulation with some base geometry for the first frame. So I'll move the constraint geometry off to the side a little bit, and then I'm going to start by creating a sphere. And I'm just going to add some rows and columns, and then we can scale this sphere down so that it's a little bit smaller. I'm also going to use a match size node and set the justify y to min just to make sure that we don't scatter anything under the ground plane. Then I'll need a switch to toggle the stream only on the first frame. I'll pipe in the dot geometry in there, and then I'll do another little expression. I'll just say $f is not $f start. So now this will only toggle on the first frame, and then it will use the simulation geometry. Moving on, let's scatter some points. But before we do that, I'll want to create a mask that we can use to control where on the surface we want the scatter to happen. And this is where you can get a bit creative, but for this one I'm going to append a mask by feature node. In the mask by feature, I'm going to up the number of samples to 8, and then I'm going to switch the blur influence type from connectivity to proximity. We can also remap the mask, but we'll tune that later. Next, I can create a scatter SOP, and in the force total count, I'm just going to set this to 2 for now. So every time the Vellum sources new geometry, it's going to spawn 2 new objects. I'll also turn off relaxed iterations for now. And then I'm going to check the density attribute, and I'm going to change this from density to mask, which is what the mask by feature creates by default. So every point will also need to have a unique ID, and we can do this by dropping down an enumerate SOP. And I'll switch this group type from primitives to points. And then we can call this source ID. Now, the problem we currently have is that this source ID will always return the same 2 IDs on every Vellum interval. So we need to find a way to count this ID up each time we're emitting new points into the system. So I'm going to drop down a new wrangle. I'll call this init PID for point ID. First, I'll need the current frame number. As mentioned previously, in my case, my frame number starts on frame 1001, so I want to normalize this first. So to recap, we're taking the current frame number and then we're just offsetting it by 1000. I'll then need the interval, meaning how often we're emitting new geometry into the simulation. And this is currently set to emit on every other frame, so I'll put in the same interval number that we defined in the Vellum source node. And I'm also casting it as a float. Then I need the total amount of source points. And we can easily grab this from the current geometry screen we're working over using the endpoints function. I also want to count how many times we've emitted new geometry. And we can floor our frame number divided by our interval. And then we can write this out to a new attribute called PID. And we want to take the source ID, and then we want to add the count times the total amount of points. So now if we bypass this switch and go over to our geometry spreadsheet, we can see that we have a PID number, and this counts up every time we're emitting new geometry. We also need to set a name attribute in order for the copied points to know which instance to grab later on. I'll start by creating an object merge node so that we can bring in our instances. Then in the wrangle, I can bring in the total amount of instances using the endpoints function again. For this example, I just want to grab a random instance, but you can obviously adjust the logic here as you wish. So I'll start by defining a random variable, and we can do random based on the point ID plus our frame number. And then we need to multiply it by the total amount of instances that we have. Then we can take this random value and floor it to make sure that we get whole numbers. And lastly, we can set the same name assignment the way we did in SOPs. So s at name equals piece plus I2A. So if you take a look at the geometry spreadsheet, we can see that we now assign a random number next to the piece string. And because we're referencing the instances, it'll adjust automatically depending on how many instances we have in SOPs. Let's also add some random rotation. We can do this by dropping down a attribute randomize. I'll set the name to be orient. And then I'm going to change the dimension to 4. I'll change the distribution to inside sphere. And we'll also use that same random PID attribute to drive the seed. So the idea is that these Vellum objects will scale over time. So before they get emitted, they need to be scaled down. I can drop down another attribute wrangle and adjust the P scale. Important to note here is that we can't really set the P scale to 0, as that will make the Vellum solver freak out. I found a value of 0.1 to work well in my case. I'll also add a point relax node to avoid a scatter to spawn points that are too close to each other. And in here, I just need to make sure that we enable relax in 3D space. Next, we can append the copy to points up, and here we need to enable the piece attribute toggle in order for the copy to points to pick up the corresponding instance based on the name attribute. So now if I play here, we can see that it's just toggling random geometry. I'll then need to unpack the geometry as we'll be adding Vellum constraints. And I want to make sure that I transfer the PID attribute as well as the name attribute. And I'm also going to go back to my copy to points op and just remove this hat from the orient attribute, because I actually want to transfer this as well. And we'll use this later when we point to form the actual render geometry. So now we can finally add our Vellum constraints. So I'm going to drop down the Vellum configure tetrahedral sub, and this will create the necessary constraints for us. In here, I'm not going to change too much. I'm just going to change the stiffness scale factor to 0.1. Everything else I'll leave at default. On the geometry stream, I'm going to add a edge attribute and just set it to be default at 0. And then I can create a null, call this out underscore geo. And then on our constraints, I'm also going to create a null, call it out cons for constraints. And here I want to make sure that I attribute transfer over that PID attribute that we created. And the reason being that this PID attribute doesn't exist on our constraint geometry, so we need to transfer that manually from our Vellum geometry. And before I forget, I don't want to create new tetrahedrals, as we've already created them, so I'm just going to delete this one. And then I'm going to pipe in the switch again. I'm also going to drop down a null. I'll call it out source points. And the reason why I do this is because we're going to need these spawning points when we deform our final geometry. So now when we got this, I'm going to head up one level And back here in the ops, I'm going to go to my Vellum source node. And then I'll want to reference those two nulls that we created in the SOP solver in order to source the Vellum geometry and the constraint geometry. I'm also going to create a new SOP solver. I'll make sure to toggle use external SOP, and we can get these by just dragging in the previous SOP solver and then navigate to the out source points null that we created. And then I'm going to give this geometry stream a separate name. And if we go back to our Vellum source and change the emission type from only once to each frame and hit play, we can see that we have continuously emitting geometry. Although now it's going all crazy. Now let's set up scaling. First, I'll drop down a merge node, and then I'm going to drop down a geometry wrangle. And in the geometry wrangle, I'm going to increment our edge attribute by our timing. And then what I need to do is change the data binding. And we want to run this over the constraint geometry and not the regular geometry. And I also need to change mode from points to primitives. And then I only want to run this over the stretch group that is being created by the Vellum tetrahedral constraint. And as I'm doing this, I'm realizing that I need to initiate the age attribute on our constraint geometry and not our regular geometry. This probably doesn't make a difference, but just to be safe. And this needs to be a primitive attribute. I'm going to hop up back to the ops, and then let's copy this geometry wrangle. In the second wrangle, we'll first create a variable that will be between 0 and 1, and this will drive the scaling properties based on how long the source Vellum objects have been in the sim. So I'll make a new variable, call it mask, and then we want to remap the f@age attribute. So the start value will be at timing. In the input maximum, we can set the length of how fast we want the objects to scale up. For now, I'm just going to set this to 1, and then we want to make sure that we're remapping this to 0 and 1. I can then add some easing to the mask using this move function. This is optional, but we can also add a ramp if we want to time remap how fast it should scale. And then I'll store the mask as an attribute that we can reuse later. I also want to create another attribute based on the same mask that will control the rest scale of the Vellum constraints. I'll start by defining a slider for the maximum rest scale. Then I'll create a new attribute and remap the mask to be between 1 and the maximum rest scale. And then through trial and error, the maximum rest scale that I ended up using was 2000. Now when we have these animated attributes, we need to apply them to the actual constraint geometry. I'm going to drop down a Vellum constraint properties node. In here, I want to check this group field and make sure that we're only running this over the stretch group. And then I'm going to enable the stiffness, and I'm going to enable the rest length scale, as well as the use Vexpression. In the Vexpression editor, we can then use that rest scale attribute that we created, and this goes from 1 to 2000 in our case. And then I also found that as the objects scale up, they'll get stiffer. So what I also ended up doing was to decrease the stiffness the bigger they get. So we can grab the stiffness and use a lerp function to mix between the original stiffness and a smaller stiffness value. And the mixing will be controlled by the @ScaleFactor attribute that we created, which goes from 0 to 1. So in practice, it'll decrease the stiffness as the geometry gets bigger. Now I can hit play, but you can see that we have an issue here. We have a lot of intersections, so that'll be the next thing that we'll figure out. Aside from that, I also don't want this necessarily to be running on every substep, so I can copy this gas intermittent solve node. Okay, now to the tricky part. So here's the issue that we have. By default, the scatter stop will add points that are right on the surface. This means that when we later copy the instance geometry, we'll get intersections between the newly emitted geo and the already simmed geo. So what we need to do is push the scatter point away from the surface. For this, we need the direction, which we can get from the normal of the already simmed geo, as well as the amount for how much we should push the point away. If you remember, we did create the diameter approximation earlier in SOPs, and this is what we'll use the diameter for. Now in order to know which object's diameter we need to use, we'll match by the name attribute so that we can fetch the right diameter for the specific point. So let's see how we can do this. I'm gonna jump back down into our SOP solver, and then right before the point relax node, I'm gonna give us some space here. So I'm gonna add a new attribute wrangle. And first we'll want to compute the radius that we'll use as the factor for how much we want to push the point. I'm going to base this off of the approximated diameter that we calculated in SOPs, and we can fetch the diameter by finding the correlating piece from the name attribute. So we can use another function called findAttribVal, and this finds a primitive point or vertex that has a certain attribute value. So I'll drop down a object merge, and in here I'm going to drag in our instances. And I'm also going to copy this one, and we want to bring in the surface as well. So with this function, findAttribVal, we find the matching piece. And then we can say that if match is less than 0, just return. And this makes sure that we get a match. From this, we can then fetch the diameter. So I'll create a new variable called diameter. And then we can do a point function. And the attribute that we want to fetch is diameter. And we're going to fetch that from the match that we find. And we also need to account for the piece scale on our points. Then from this diameter, we can calculate the radius. And that's just going to be half of the diameter. And if we want to, we can also add a little bit of padding if necessary. Next up, we'll need to sample the direction from the surface of the simulation geometry. We can do this with the xyz_dist function. I'll start by creating some variables that the xyz_dist function will write to. Then we can create the xyz_dist. And what we want to sample from is the surface, or the simulation geometry. So that's going to be the second input stream. And we want to sample from our current position. And then we need the primitive to write to and the UV'. Now when we have this, we can sample any attributes that we want. In this case, I'm going to sample the normal, and that will be our direction vector. And then just to be safe, I'm going to normalize this as well. In some cases, I also found it useful to have an up bias that we can use to skew the direction upwards if needed. So I can create a up bias slider. And then we need to create a vector for that as well. And finally, we can set the new position. So to recap, we're adding that surface normal, and then we're multiplying it by the radius, which will be the amount that we're going to push out. And then we're adding this up bias at the end. So now if we go back up in DOPS, we can zoom out a bit and hit play. And now you can see that we have a way better starting point and we get way less intersections. However, there's still a chance that we push into the geometry on the opposite side. So what I also found helpful is to check against a SDF representation of the geometry and try and resolve any further intersection by pushing the point out from the gradient of the SDF. So I'm going to hop down into our SOP Solver again. We can call this surface push. And then I'll drop down another wrangle. First off, we'll want to convert the SimGeo to an SDF using the VDB to polygons node. I'm then going to decrease the voxel size a bit. And I think I upped the exterior band voxels. And after this, I'm just going to smooth it just a tiny bit. I'll set this to mean curvature flow, and I only want 2 iterations. Then I can pipe this into our wrangle. And we can call this one SDF push. First off, we'll start by writing out the radius to an attribute that we can use in the other wrangle. And I might want to create a different kind of padding, so I'm going to do this before we apply our padding for the surface push. Then I can import this radius. And then we can add a custom padding for that as well. And I'm going to create a new variable called clearance, which will be a radius plus the padding. Up next, we will bring in our SDF. So this will be the distance to the surface. And from this, we can calculate the gradient direction as well. So with the volume gradient function, we can extract the gradient. And if the gradient is negative, it means that it's inside. And if it's positive, it'll be outside. So the idea is that we'll try to calculate a new position until we find a position that is free of intersection. And we can do this in a while loop. We'll first need an iteration counter and a way to stop the counter. So we can call it max iter for maximum iterations. Let's start by setting 8. And now let's declare the while loop. So as long as the SDF or distance is less than our clearance, and our iteration is less than our max iterations, run this code inside of this block. In here, we want to calculate the new position. So we can say vector new p, and that should be the position plus the gradient times our clearance minus the SDF. And then we can scale this by a factor of 0.5 for stability. We can then calculate the new SDF or distance. And this will be based on the new position. And then I'm also going to create a condition. We only want to accept the new position if it improves, meaning if it moves further outside. So I can write if SDF underscore new is greater than SDF, meaning it's outside, then let's update the position. And we also need to update the SDF itself, as well as the gradient. And then at the end of the loop, we just want to increment the iteration counter. So now if I go back up to DOPS once again, zoom out a bit, hit play. Now we seem to have resolved most of the intersections. So if I go back into the SOPnet, we can now further play around with the mask attribute that I mentioned earlier. So if I click this button here, we'll get a preview of our mask. And what I want to do is I want to remap the shadow mask. What I want to try and avoid is to scatter points on these areas where there's little to no space. So I can just take this point and drag it up. And now this should help resolving any points being scattered too close to other geometry. And I'm actually going to reset the number of samples, and I'll just increase the blurring iterations instead. And then something else I added was in the scatter SOP. I just added a seed based on the frame number, and I added some random value. And for my final animation, I think I went into the Vellum solver and I added 3 substeps, and I lowered the constraint iterations to 60. I'll also add a pop speed limit. I found that this helped calming the simulation even if there's some minor intersections left here and there. So we can set the maximum speed allowed to be something like 5, maybe. And this should help resolve any crazy points that are freaking out. So another important thing that I almost forgot about is to remove any interior details on the simulation geometry in the SOP solver. So if we don't do this, there's a chance that we scatter points on those interior faces, which will cause unwanted intersections. We can drop down a convert TETS node. And then if we clip this, we can see here that this just makes sure that we're removing any of those interior faces. So now if we hop back up, we should get something that's a little bit more stable. As with most challenges in Houdini, I'm sure there's better ways of solving intersections, but this is just what worked for me in this particular case. But if you have any tips and tricks on how to solve these intersections, feel free to drop a comment in the comment section. So that's it for this part of the tutorial. We now have a working sim. I'm gonna cache this out, and in the next part we'll see how we can point to form back the original geometry that we can use to render. Thank you so much for watching, and I'll see you in the next part.